Many modern broadcast facilities have moved from physical audio and video transport to IP-based technologies. In radio, that's usually where you get into audio over IP, or AoIP. What is AoIP, and how does it utilize existing IP network standards? How did pro audio technology evolve to get us here? Let's explore that today, and regardless of whether you're an audio nerd, a broadcast nerd, a computer nerd, or some odd mixture of all three like I am, this video has something for you. For decades, pro audio has been built on the back of the humble XLR connector, developed in the mid-20th century by James Cannon. Folks who are less familiar with this sort of gear will recognize this as the connector typically used for microphones, but you can double these up to get an analog stereo connection, like with this cable. Those who pay attention may notice that your stereo headphones have 3 terminals on the plug. So why don't we get 2 channels with 3 pins on a single XLR cable? The reason is simple. Professional audio signals are almost universally carried on a balanced line. Let me explain. Your headphones run what's called an unbalanced connection. The plug has 3 terminals. One is the left channel, another is the right channel, and the third is a shared return path called ground. The term ground is not so accurate these days, particularly with portable devices that can't be connected to a real earth ground. A more appropriate name would be common. Some devices use that term, but I'll just keep saying ground for reasons you'll understand very soon. The ground pin is kept at nominally 0 volts with negligible impedance to an earth ground connection. This just means that any voltage introduced to that ground line will immediately flow out and keep that line at 0 volts. Each channel signaling is expressed as a difference in voltage between its signal line and a reference point, which in this case is that ground pin. For example, a 500 Hz sine wave on the left channel will cause the voltage on the line for the left channel to swing between, for example, 2 volts and -2 volts relative to ground 500 times per second. You can apply a completely different signal with independent frequency and amplitude on the remaining terminal, and that represents the audio signal for the other channel. Since it's also measured relative to that same ground pin, that works to give 2 channels of audio on 3 conductors. This signaling mechanism falls apart in an environment with a lot of electromagnetic interference, and it gets worse with longer cable runs, which are the rule rather than the exception in pro audio. Interference from other sources of RF, whether they are intentional radio transmitters or unintentional radiators like AC power lines, will introduce what's called common mode voltage on your signal cable. Common mode is just a fancy term meaning the same voltage spike appears on all signal lines at the same time. Since we're referencing our audio signals against ground, which, as I explained earlier, will stay at 0 volts, you get interference in your audio signal. In balanced audio connections, there is a second signal line for each channel running the entire length of the cable. Instead of measuring relative to ground, the signal in a balanced line is derived from the voltage in the driven side of the signaling path relative to the non-driven side. This second line serves as a dedicated return path for the channel rather than a shared ground line, and allows the third pin to be used as a true electrical ground connection. Most importantly, this equal length in both signal lines means the impedance on both is also roughly equal. This may sound counterintuitive, but equal impedance in the 2 signal lines helps ensure any interference exists equally on both. Since any common mode voltage spikes will affect both lines equally, measuring your signal this way means the difference between the 2 will not change regardless of how much interference there is in the environment. Balanced connections can also employ what's called differential signaling, which is applying a mirror image of the signal to both lines. This not only benefits from the rejection of common mode voltages on both sides of a balanced line, it also provides a larger voltage difference between the lines, which helps mitigate losses on longer cable runs, among other things. It's important to note that contrary to popular belief, balanced audio does not automatically mean differential signaling. While many pro audio devices make use of differential signaling, they don't have to. This setup has been the standard for many decades in pro audio applications such as live sound and broadcasting. But as IP networking technology matured around the turn of the 21st century, equipment vendors began seriously considering the benefits of using this technology to get audio from point A to point B. This also comes with the benefit of digitizing all your audio, but if you want to learn more about digital audio in general, this video series by Technology Connections does a much better job explaining it than I could. With an IP network, you can utilize various techniques to create a much more flexible way to route your audio. Sure, you can keep it simple and send digital audio streams directly from one device to another, but that's not the most flexible or elegant solution. For example, as the number of devices goes up, there's a point at which you start saturating your network links, particularly if you're using multi-channel uncompressed audio at high sample rates, which is common in pro audio applications. Many AoIP standards utilize multicast technology to make audio sources available on the network. Multicast is a way to communicate to a group of devices at the same time, as opposed to the typical one-to-one communication I described a moment ago called unicast. Sources send UDP datagrams containing digital audio samples to special reserved addresses, and the Ethernet switches making up the network infrastructure forward the frames containing them to multiple ports. Less advanced switching equipment will forward multicast frames to every other port, called flooding, because the flag for multicast traffic is the same as the one used for broadcast traffic. That's not much better than a unicast setup, particularly when your multicast traffic is primarily lots of audio-visual data. However, more advanced switches can use a technology called IGMP snooping to help manage this. An important part of IP multicast is the Internet Group Management Protocol, or IGMP. It was designed primarily for routers to control which multicast streams get routed between different network segments, but it has an important application within network segments having large numbers of multicast listeners as long as the switches support it. Switches supporting IGMP snooping can tell the difference between multicast and broadcast traffic, and they typically do not flood multicast frames when it's enabled. Devices needing to receive data sent to a particular multicast group will first send a membership report to the multicast address for that group. The network equipment hears this message and begins either routing the requested multicast data to that network segment or forwarding frames to the switch port the request came from, depending on whether the network device is a router or a switch. Multicast routers periodically send membership queries out to the network, and listeners must respond to continue receiving the multicast traffic they're interested in. Switches that support IGMP snooping keep track of where these queries are coming from and make sure any membership reports get forwarded there. Some switches will even serve as a proxy and aggregate these membership reports because, from the perspective of a neighboring network device, multicast traffic is sent on a particular link in the topology only once, regardless of whether there are 2 or 25 listeners connected. On completely isolated multicast networks without a router, which is common in audiovisual applications, switches supporting IGMP snooping can also be the designated querier on the network. When a multicast listener no longer needs to receive data for a particular group, it can simply stop processing the datagrams and stop including the multicast address in membership reports. The network infrastructure will eventually, typically after the next membership query interval, stop sending the data to that switch port. However, in environments where it's more efficient to make that process faster, newer versions of IGMP allow a listener to send a leave group message to a specially reserved multicast address, and infrastructure equipment should stop forwarding multicast frames immediately. There are a few other implications to keep in mind when planning, implementing, or maintaining an AoIP network. Like any other multicast network traffic, AoIP must make use of UDP rather than TCP because the connection-oriented nature of the TCP stack doesn't work with one-to-many communication. This constraint makes it important to have robust switching architecture. While multimedia content can generally handle packets that don't make it, you want your audio network to be reliable. Most AoIP standards make use of differentiated services, or diffserv, so your network equipment needs to support these quality of service features. Ideally, an AoIP network not only has infrastructure that understands IGMP and diffserv, but is also completely separate and isolated from your normal LAN and internet traffic. As with any digital audio installation, there also needs to be a mechanism to distribute a clock signal. If you haven't done a lot with digital audio or computer science, that doesn't mean each device really wants to know if it's 5 o'clock somewhere, but rather each device needs to synchronize to the same ticks from a high-quality oscillator. When most people think of distributing any sort of time-based data over a network, they'll think of NTP, the Network Time Protocol, which can reasonably get a clock synchronized to another within less than a second. However, when you're sampling audio signals 48,000 times a second, that won't make the cut. Fortunately, you can get an extremely accurate time signal from atomic clocks. Of course, the atomic clocks I'm talking about are approximately 21,000 kilometers or 13,000 miles above your head, aboard navigation satellites like GPS or Galileo. In essence, all these satellites do is continuously broadcast two things: what time it is down to the microsecond, and precisely where the satellite is. This doesn't mean you have to put a sat-nav receiver in every audio device. IEEE 1588, better known as the Precision Time Protocol or PTP, can yield much more accurate synchronization than NTP, and all you need is one reference clock on the network with GNSS capability. Just about every AoIP standard will use PTP as its clock source. Of course, you can use PTP without a satellite reference, but on a production network, you'll want to have one. The audio over IP standards commonly used in broadcasting include Livewire by Telos Alliance, WheatNet IP from Wheatstone, and Ravenna, an open standard originally developed by engineers at Lavo. Other standards that see use in live sound applications include Dante by Audinate and QLAN by QSC. Most of these standards, whether focused on live sound or broadcast, adhere at least in part with the AES 67 standard published by the Audio Engineering Society, so devices using different AoIP implementations can interoperate to an extent. In turn, AES 67 was used to define the audio portion of SMPTE ST2110, the standard applying IP transport of video signals in television production. Professional audio has come a long way, and the implementation of real-time audio transport using IP networks is just the latest, and possibly the last, major evolutionary step. We'll continue to explore AoIP and how it's used in broadcast in future videos when it's relevant. Until then, be sure to subscribe and light up that notification bell so you don't miss more stuff like this from me. You can visit my landing page at broadcastblueprint.com. I'll catch you next time.